Thank you. All right, so I'm Bram. I am co-founder of Chia Network, and we are aiming to make a second generation cryptocurrency, so we're trying to make something better than Bitcoin. And our focus is very much on hard fork things right now, because you get one chance to do all the hard fork stuff and then never again. So we're going to have a no hard fork policy after initial launch. So our biggest technical lift is switching from proofs of work to proofs of space. I'm not the first person to think of this idea, but it's hard to get it to actually work.
Hi.
So,
You want this?
oh, I have a microphone.
Better?
Is this better? Okay. All right, I'm going to move the mouse pointer out of the way. There we go. So, the first thing to understand is why to do this. I gave a talk at Bitcoin Devs quite a long time ago now about how you can't really get rid of the waste from cryptocurrencies. It's inherently baked into the whole thing. And at the end of that, I was like, yeah, maybe if you use some ideas that I have and some ideas that other people have, you could maybe get proofs of space to work. Because it's this interesting loophole. You're still, in some sense, wasting a resource, but you're wasting a resource that you were already wasting. There's already all this storage media out there, and a fairly significant fraction of all the capacity and all that storage media isn't being used for anything. So if people can leverage that in a way that has essentially no marginal cost on what they're doing on top of it, and the amount of rewards are less than the expense that people already put into that storage media, then you have this loophole in proofs of work. And this appears to be entirely doable from an economic standpoint. Storage is an over $100 billion a year industry. So that would be an awful lot of farming rewards to overcome even a small fraction of that. So it's hard to get this to actually work. There are two pretty big whole classes of attacks that you have to worry about here. And they're directly related to the things that make proof of space good. You made it not cost anything for somebody to farm, so they can then go, all right, well, I'm just going to try lots of possibilities. I'm going to try every possibility. I'm going to just grind on this, and until I find something which is very favorable to me, and I'm going to go with that. And then you're basically just back to proof of work again. Proof of work avoids grinding attacks by just saying, nope, that's just what you do. You grind to mine in Bitcoin. That's what Bitcoin mining is. You're printing lottery tickets, and that's it. But for proofs of space, you're specifically trying to avoid that. You're trying to get rid of it. You're trying to make it so that the only resource here that people are using is space, and they have no real option to use anything else. So how to fix this? But before we talk about how to fix it, there's a whole other class of attacks that you have, which is someone can not only grind going forward, they can rewrite history. They can go back some amount of time and redo all of that to look better than they want for them, for whatever definition of how they want things to look. And in the extreme case, they can go all the way back to the beginning of time. They can say, this thing's been around for 10 years, and I'm a 20% miner today, but I'm 1,000% miner as of a year ago because the capacity in the system as a whole has been exploding. So I'm just going to make a whole new history, starting from the beginning of time, and my chain will have a greater weight than the legitimate one. So this is not good. You don't want that to happen. These attacks actually, the proof of work doesn't really have grinding attacks, just kind of by definition. But it definitely has history rewriting attacks. The things that are stopping it from happening in Bitcoin are kind of interesting. One of them is that you actually have a lot of upfront costs to start mining Bitcoin. You have to buy your ASICs to start to have everything up, which is a significant initial investment. And basically all the ASICs that are out there are running today. There's some old ones which are not capitally efficient to run anymore that you could probably get for almost nothing, although there's no secondary market in that right now. That's actually pretty alarming that it's possible to do that, because if you were willing to eat costs to rewrite history, those could totally work. A lot of miners have quite a bit of cryptocurrency held up, so they aren't really keen on doing things that might tank the value of it. That appears to actually be a lot of what's going on with why we're not seeing history get rewritten in Bitcoin. And also the amount of scams you could pull off isn't that great, because Bitcoin is a very cash and carry thing. So your leverage on being able to unroll transactions isn't all that huge. But as more smart transactions and stuff happen, this is likely to get worse in the future. And the thing that's really scary is just how easy it would be for someone to launch an attack. I believe it would take 4 mining pools currently to do a 51% attack on Bitcoin, which is extremely alarming. And one of the big reasons why it hasn't happened is because right now block rewards are quite a bit larger than transaction fees. But in the future, that will invert, and we're likely to continue to see this behavior where transaction fees come in spurts, where there's like an hour with high fees and then it goes down to nothing as the mempool gets basically emptied out. Thanks to, we can actually see this happening now because a real fee for transaction fees has developed. Bitcoin, this was a matter of considerable controversy, and all the Bitcoin core people were like, okay, well, we're just gonna let people eat it until they fix their systems to no longer be wasteful on the blockchain, and then fees will go down, and that's exactly what happened. Although people had to eat it for a while with high transaction fees for that to happen. But nothing like a good monetary incentive to make people fix things. But if we continue to see these spikes, you're gonna have a situation where like fees were pretty high an hour ago and now they're basically nothing, and anyone who's got substantial resources, it's way, way better for them to just rewrite the last couple hours of the actual workday of fees going through rather than try and mine blocks moving forward overnight. And that's extremely alarming, how likely it is for that to become widespread in the future. All right, I'm going to rant a little bit. Which is so unlike me. There's this term called nothing at stake that's used to talk about problems. The term nothing at stake is proof of stake propaganda. It describes problems that happen when you're not doing proof of work. However, it's not a description of what the problem is. It's a description of a solution to the problem, and it's a solution involving stake. What you really want to talk about are grinding and rewriting attacks, although they are misleadingly referred to as the nothing at stake problem. And as soon as you adopt stake at all, you've immediately massively reduced your security model in the system as a whole, and all kinds of problems come up. I'll get to those. I'll get to those right now. Proof of stake sucks. So all these problems start happening. First of all, proof of stake is not a truly decentralized system. Bitcoin is a database that anyone can join or leave at any time. Like everyone who's currently doing Bitcoin mining can simply disappear, and new people can join, and the system will continue to work in the future. Proof of stake doesn't work that way at all. Proof of stake is at best a kind of decentralized centralized system instead of a decentralized decentralized system. As part of that, proof of stake needs to have some threshold to have a quorum. That is the number of participants necessary to vote to move things forward in the future. If the size of a quorum is too small, people can attack the system and rewrite history. If the size of the quorum is too big, you can't actually make anything happen. as a matter of practice, if you start running numbers, it turns out these cross in the wrong way. They're on the wrong sides of each other. There's a range in which you can neither reliably move forward, nor can you reliably be sure that people are just going to attack you for your quorum sizes, instead of there being kind of a sweet spot. On top of that, when you say nothing at stake, that means that this implies that the solution is to put something at stake, meaning that you have bonding, where whoever bonded puts their shares at risk. Why should somebody do this? I don't know. Doesn't seem to be a good answer for that. And there's a good reason for them to not do it, which is you have slashing. Once someone has bonded, you want them to not be able to just make off with the goods, and so people add in slashing, which is defined punishments for bad behavior. Of course, once you have defined punishments for bad behavior, people can start running scams where they screw over other people by making them get punished for bad behavior, which they weren't actually participating in, or making it look like they were participating in bad behavior. So this is a bad thing, and gives a pretty strong disincentive to bond. And if you try and create incentives for bonding by doing direct rewards, that creates all kinds of other huge issues where people can just outright steal bonding rewards over other people. That just creates 51% attacks on purpose. You can, in principle, avoid a situation where somebody causes you to get slashed just by being extremely judicious about never ever like engaging in anything that can kind of look like bad behavior, like never doing a double vote and stuff. Of course, to do this, you have to have your machines like never go down, never get hacked, and also there just can't ever really be any substantial reorg that happens. Or it looks like you're engaged in bad behavior supporting this reorg. And even worse, if you have a split for some period of time, you can get into a situation where there are now 3 versions of history for the last couple of blocks, no single one of which forms a majority, and so in order to move forward, someone has to take one for the team and do a double vote for something different than they voted before, and then they're going to get slashed. Slashing really kind of looks like a poll tax. It's like if there is a poll tax, there's no reason to vote unless you're trying to pull some shenanigan with your voting, and that's a problem. On top of all those other problems, you have this highly technical issue that really what you're trying to do is K-agreement. It's actually a much more complicated version of K-agreement, and it turns out K-agreement doesn't really work, can never really work quite right, for very technical reasons. And it's worth noting that all these things that I've said aren't really specific problems. They're categories of problems, like whole sets of types of issues rather than a specific thing you can attack straightforward. And those things were stake, bonding, slashing, checkpoints, and K-agreement. Oh, I didn't get into checkpoints. They also suck. So once you get through this, you know, there's a saying, when you find yourself in a hole, stop digging. Maybe proof of stake just isn't a good idea. Maybe there's a reason why nobody developed this proof of stake system before Bitcoin came to be, and it's because proof of work is just inherently better than proof of stake. All right, so if we're not going to fall for the proof of stake propaganda, how are we going to combat grinding and rewriting attacks? So this is entirely in the context of assuming that we're going for proofs of space as the only other type of resource that it seems we can use in a reasonable way. So the first idea is we're going to add proofs of time to the thing. So we're going to not only have proof of space, we're going to have verifiable delay functions, aka proofs of time, and we're going to alternate between the two of them. I'm going to get into that. Next, we're going to try and stop grinding the straightforward way, which is just remove all the sources of malleation that are available for people to grind on. So we're going to split the blockchain between the trunk. Why is this flickering? It's so annoying. We're going to split the blockchain between the trunk, which is the thing that contains the challenges and responses to challenges, and the foliage, which contains more stuff. In particular, it contains all the transactions. Transaction sets are trivially malleable and absolutely should not be factored into challenges because if you do that, you've just got grinding all over the place. The only things that should be going into the trunk are proofs of space, proofs of time, and once in a great while, a work difficulty reset. Those are the only things that go there. Another thing to do is make everything canonical. That is, there's only one way to represent something. So our proofs of space, our verifiable delay functions, our signature types, and the ways we derive new blocks should all be canonical formulas. So, this sounds good. The only things we have left to do now are invent a new proof of space algorithm, because there wasn't previously a nice canonical one in the literature. Also come up with a new verifiable delay algorithm, because there wasn't previously a good canonical one in the literature. And figure out how to combine them, which there's also nothing in the literature on how to do that. So, minor issues. All right, so the proofs of space, what a proof of space does is it's kind of like you fill your storage media up with bingo cards and sort them. And then a challenge comes in and you find the closest bingo card that you have to that thing. And whoever has the closest bingo card wins. It's actually much more complicated than that for technical reasons, which I won't get into. I've been working on that a lot recently. We're also, for our signatures, we're probably not going to be using straightforward signatures. We're going to use some zero-knowledge magic so that our signatures are non-outsourceable. You can use basically anything with any property as a kind of perverse type of signature using a zero-knowledge thing, and we want non-outsourceability for its own reasons. Non-outsourceability is this other big feature where if someone tries to run a mining pool, they can collect partials from people, but they have no way of guaranteeing that someone who's sending them partials doesn't just make off with the goods when they find an actual block in a way that's totally undetectable. And zero knowledge is a nice tool for doing that way, because zero knowledge is all about hiding what it was you actually used. So that does a good job of making it so that we don't have any malleability issues with the signatures. I kind of fumbled my words on that slide here. Also, a really important and subtle thing for the proofs of space. You can always attack a proof of space just by regenerating your whole plot over again and doing a search on it and then regenerating the whole thing again and doing a lookup on that. This is inherently an attack that can be done, although relatively expensive and hard to do with low latency. But it should be that the time-space trade-offs available are as close as possible to one of two options. You either are repeatedly regenerating the plot and doing a lookup on it every single time in response to just one challenge, or you pre-generated your plot and you just do one lookup on it. Those should be really your only two options. And it's pretty hard to make it so that people can't be really cute and figure out very clever ways of using extra CPU to squeeze more utility out of their space. The Beyond Hellman paper gives a reasonable construction for this. We've come up with a whole bunch of implementation details and improvements on that, which are not yet published. Turns out we're going to be using a fan out of 3 and other stuff. So that's what we need out of the proofs of space. What we need out of the proofs of time, first off, the question of what a proof of time is. A proof of time needs to be given a challenge and a number of iterations to run through. And it should require that if you double the number of iterations, you double the amount of real wall clock time it takes to be able to compute this thing. The ratio, you don't know. That's what work difficulty resets are for, but it needs to increase the depth proportionally to that. And it needs to be that the output of this thing is a short solution, a value in response to the challenge, and also it needs a proof of that solution being accurate. The proof can be malleable. It's okay if the proof is malleable. And both of these need to be short, and there must be an algorithm for verifying that the proof is valid very quickly. And it should be infeasible to find a proof of an invalid solution, even in a way which takes roughly the same amount of wall clock time as the original thing, because that would be a source of grinding attacks. There are a number of constructions based on secure hash algorithms, including one which we just published and got this paper in Eurocrypt for, which unfortunately are not applicable to this. All right, and then after you have those things, you have to hook it all together. So the high-level idea here is you're alternating proofs of space and proofs of time. So everyone finds the closest bingo card to the challenge from the last block. They take that distance, the distance between those two. It's not actually doing this, but let's pretend. And then multiplies that by the current work difficulty factor, and that tells you the number of iterations which the proof of time needs to do. And because of that, the best one will finish first in terms of real wall clock time, and you'll be able to extend off of that before the other things. And this makes it so the only discretion that the farmers have left in terms of being able to grind on things is they have the option to not publish something. They can work off of an inferior proof of space, although that will require a longer proof of time and hence will be inherently behind right off the bat. Also, there's subtleties with work difficulty resets, which I'm not going to talk about right now. So it turns out that as long as you have the property that an attacker cannot generate other people's proofs of space based off of what they've done before, then they have no ability to slow someone else down. They can extend someone else's chain to claim rewards off of it, but they can't destroy someone else's chain by maliciously publishing things which cause someone else to actually extend more slowly. And using that zero knowledge magic fixes that problem very nicely. This is the no slowdown lemma that's in an upcoming paper. So, how does this do? Well, in terms of avoiding rewriting attacks, we've actually won. We totally won this battle already. If an attacker wants to rewrite history since Genesis, or even since an hour ago, they have the same problem either way, which is they're perfectly free to rewrite history, and it won't cost them a lot of resources to do so. It will if you want to rewrite the last 10 years of history, you can do it using only 10 years of CPU time. The problem is it will require 10 sequential years of CPU time. It will take 10 real years to do it at your full capacity, and the weight of your chain is falling behind the legitimate one, which is growing faster than you're growing your own thing. So that is not a useful thing to attempt to do, and this whole proofs of time thing has basically totally fixed this problem for us. Grinding attacks, since we've thrown in all these other doohickeys, we've done a pretty good job of stopping them. The only thing that's left is an attacker can work off of alternate histories where they start with worse proofs of space previously. And they can just try every single history that they can do, although the ones that aren't the very best one start out a little bit behind. So there's this question of how effective is this? And the answer is really actually quite surprising, which is even if an attacker now works off of every single branch that they have, they try every single response to every single challenge and just have infinite numbers of proofs of time running, the amount of extra value they can squeeze out of the space that they're allocating is actually a small constant factor. It's actually E, which is a little bit less than 3. This is sufficiently counterintuitive that we've both done extensive simulation and actual formal analysis of it, and it is true. I don't have a good intellectual justification of why it's the case though. So we need to do something about this, and it turns out there is a pretty simple thing we can do. We can, in the same way that proof of work embraces grinding, we embrace this to a limited degree. So we decide, well, the honest chain isn't just going to work off the top head, it's going to work off the top, some number of them. And so the ones a little bit below the top have a chance to catch up. And this will reduce that factor from E to something smaller. And this is just kind of a social convention that we're going to decide what this number is. We can increase it later if necessary. But it turns out a value of 3 does a pretty good job. You've gotten most of the benefits of doing this out of setting the value to 3. So we're going to start with that. At some point in the future, we might crank it up. You can always crank it up. Very hard to crank it down. So that's the high-level view of proofs of space and time. People have done a lot of different types of proposals for proofs of whatever, and most of these are really astoundingly horrible, like truly amazingly horrible. So, as a matter of benchmark to compare this against, I would like to propose a type of proof which most people would say that's probably not a good idea. I'm specifically going to compare the general problems here that happen in almost all these things with proofs of bigger dick. So, proofs of bigger dick, you take a neural network and you train it against a corpus of dick pics and quality measures for them. And this is fixed, it's what you use later on in the system. And guys post dick pics to the blockchain, and the better ones win, and that moves it forward. I don't know how many of you might be excited about how much stuff you could get off of this. Now this has, this is actually right off the bat a much better idea than most of the other types of proof that people propose. Because it's locally auditable. There is actually a defined function that you can run through, and it will tell you what the quality of the blockchain is. Unlike proofs of participation, importance, more nodes, and I don't know what the fuck else, which are not auditable at all, and so if you're a node that's trying to join and you haven't been literally on the network since the very beginning, you have no way of actually joining in all those systems, which makes them really terrible ideas. But proofs of bigger dick definitely qualifies for that one. It's also actually doing pretty well on the utility of its proofs. Most of the useful proofs of work that people are proposing are not actually for very useful things at all. They're for completely artificial things that nobody cares about, and there's definitely a market for dick pics. Probably a bit oversaturated, but that is a very real...
Is there though?
There are websites dedicated to these things that seem to be well trafficked. On other metrics, it doesn't do very well. The scoring functions that we can generate currently don't correlate very well with the intended value. Basically, anything that's image recognition on a deep learning system, if you are given the final trained neural network, it is very easy to generate things that just look like noise, that look nothing whatsoever like the intended things that score very highly on matches. Also, the distribution of the quality of outputs isn't very good. In order to get block arrivals and such to happen when they at the distribution you want them to, you want a nice exponential distribution of the quality of outputs, and you want things that are very near each other to not all be very good solutions. You don't want to be able to twiddle a pixel or two and get something that is very similar quality to what you had before. And so proofs of bigger dick totally fails along those ones. But there are other metrics on which it's actually quite good, because the system as a whole is not asking users to supply challenges which people then use for proofs of whatever in order to create blocks. If you had a system which was, generalized fetishes, so someone could, like, I don't know, ask for a picture of a three-titted whore from Mars, then someone might happen to have, from Total Recall, a particularly good picture of a three-titted whore from Mars, and simply request that on the blockchain and then provide it themselves and get a block that way. Actually, the generalized fetishes one actually isn't all that bad compared to proofs of storage that people talk about, which is a really terrible idea. With proofs of storage, so with the generalized fetishes one, at least the person who wanted to supply the picture of the three-titted whore from Mars would actually have to still have that picture around. With proofs of storage, someone can provide queries for data which they have a cryptographic seed for, and they don't need to keep the data around while everyone else does. And so they get a tremendous advantage there, and this is completely not detectable because all this data is supposed to be encrypted anyway. So basically, proofs of storage is the absolute pinnacle of worst ideas for proofs of anything, except for, like, well, the participation and importance in more nodes are pretty terrible too. So it's really kind of a stiff competition and really bad ideas in the space here. But the upshot is, the vast majority of proofs of anything are just terrible. All right, that's all the presentation I have. I know you were really enjoying me talking about dick pics. But I can answer questions now, if anyone has any questions.
I'll get a mic around. We actually paid Dial on extra to bleep all of that out. Post it on YouTube.
So every time you finalize a block, you do this patch, you calculate the pattern, store it, and then come back and look at the numbers.
Patch?
It's the stuff that you write on the space, on the disk.
When you need, when you do a proof of space, there's a challenge. It's basically the hash of the last proof of time that came in, and doing that, calculating the response is very fast if you've pre-calculated stuff on disk. It's a couple of lookups on disk to figure out at least the quality of your output. So that can be done at very, very little additional cost once you've done this allocation up front.
So how long does it take for the transaction to finalize?
Oh, the block times here can be mucked with. That's a different design decision. We're going to go probably with 5-minute block times on average. And the distribution of arrival times is exponential fall off, same as it is in Bitcoin.
Thank you.
Who else? Questions?
So you said that it's combined with proof of time. So is proof of time already developed, or is it?
We have a plan for our verifiable delay functions that we've mostly worked out. Ben Fish gave a talk at BPACE talking about that. Mm-hmm. We've done some iteration on that since, and we're working on it. The new developments in proofs of space and our specific plans for VDFs and an explanation of how to hook this all together will be the subject of papers to be published in the future. We're actually sticking with like actual papers in refereed journals and stuff for things and not writing white papers, because white paper is a term for something that's in a paginated format, as far as I can tell, is the definition of a white paper.
Oh, and what's VDF?
Verifiable delay function.
Oh.
It's a more technically specific and accurate term for proofs of time that lacks the poetry.
Question? One and then two.
What kind of ZK magic argument protocol are you using?
So we're actually using two different zero-knowledge things in two different places. We make jokes about it being Chia University, because we're spending a lot of time studying, actually. The verifiable delay functions are probably going to use snarks for the proofs. They're not super dependent on those. I mean, they're not absolutely dependent on those because they can be calculated without running through the proofs, but it's a good idea to have them because the proofs are fast with snarks. For the signatures, the general idea is that anything with any properties at all can be used as a very perverse kind of signature if you're using a zero-knowledge system, because someone can create a message giving some string that has some property that you want it to have, plus the value you want to sign in clear text, and they do a zero-knowledge proof that this string exists and reveal what it is that the thing contained in clear text was, which is this interesting insight into how zero-knowledge things and signatures are related. For what we're using, we're probably going to be using bulletproofs for that.
Right, I was going to ask
Yeah, probably bulletproofs, and we're probably going to be using mimic for the secure hash function that's needed in our proofs of space because it bulletproofs nicely. We're going to be using bulletproofs don't seem to be the best solution for our VDFs because that one needs to be extremely performant because it needs to keep pace with the underlying VDF that you're doing. You do this thing where it's multiple iterations and you're using an underlying VDF and there's this old square root and a group thing that's published in the literature that isn't quite good enough that you can iterate, and the idea is you use the factor that gives you to make it so that the snark that's verifying it can outrun it. And there are a few clever tricks you can do where the snark can run fast because it's working on the same underlying group as the VDF is, and it needs to be this weird thing where snarking together two snarks is efficient as well. But this can be made into a nice small circuit if you're clever.
I'm sorry, I have one last follow-up. I'm not sure how this is going to land, but so for the bulletproofs, I usually have this discrete logarithmic assumption for the commits. Like that's fine for classical computers, but I'm reading that like for quantum adversaries, it doesn't really hold well. Like.
Yeah, I'm not worrying about quantum.
Okay,
so.
okay, got it. Okay.
Any other questions on this side? I'll be back. You? Yeah.
Technically, not a technical question, but there was a post going on Twitter saying that around the time 2008, 2009-ish, when Bitcoin was invented, your online activity came down and people were making claims that you are Satoshi.
So the reason why my online activity went down during that time, I was actually working on BitTorrent Live, which is this really fabulous, amazing technology, which is not publicly available for really frustrating, stupid reasons right now. But if I had been Satoshi, I wouldn't be having to clean up the fucking data formats of the blockchain. It's really a gigantic mess.
You said you have a no fork policy. Was that sarcasm?
No hard fork policy.
Okay. Can you elaborate more on that?
Hard forks are a bad idea. So there's this distinction between hard forks and soft forks.
Yeah.
So a hard fork takes something that wasn't in the past a valid blockchain and makes it valid. A soft fork takes something that was in the past a valid blockchain and makes it invalid. Soft forks are very easy to do. You just get enough adoption that any blockchain that it supports them will get quickly orphaned, and everyone in the entire ecosystem who worked before will continue to work after a soft fork comes out. Hard forks require like pretty much a flag day of everyone coordinating in order to be able to make them work, because they make it so that people who were speaking the protocol just fine find it's changed out from under them, and they start rejecting the thing that's supposed to be the valid blockchain, and inevitably results in like the Ethereum Classic split, where there's some subset that are working off the old thing and others who are working off the new thing. If you claim to be able to issue hard forks at will, you're really not talking about a decentralized system at all. You're really talking about a centralized system, nudge, nudge, wink, wink. Like, you know, oh, it's decentralized except we can change it all whenever we feel like it. That's not very decentralized at all. And seems to be missing the point. So at Chia, we're going to be following the Bitcoin model, which is you just don't do hard forks. And it turns out you can do a really surprising amount of stuff with soft forks, like more than people thought in the past. But there are some things that really well and truly do require hard forks that are really not obvious up front. And I'm very focused on those things at the moment. So our big features right now are swapping out the consensus algorithm, the proofs of work for proofs of space and time, adding in non-outsourceability, and cleaning up the transaction format, in particular changing the way in which transaction IDs are calculated so it doesn't include way more information than it should, which it does in Bitcoin. Those are things that really require hard forks. The only non-hard fork thing we're really doing right now is we're switching to BLS signatures everywhere, which is technically a soft fork, but kind of a gigantic mess. So getting that in right off the bat.
I'm kind of new to proof of space, but can you actually store something like?
No, this is not proof of storage. This is utterly useless stuff that's being done. It's just meaningless bingo cards. There is some proof of space. There are some proof of space algorithms which are fascinating, which can use catalytic storage. So you are proving the space, but there is something useful actually being stored there, and that can actually be most of your space. They unfortunately are highly malleable and really, really complicated, so they're not appropriate for what we're doing here. And it's not like you can randomly access that stuff. They wind up having these weird properties that like you can write to them quickly, but you can't read from them quickly. Like if you want to get the data out, you actually have to do like a pass over the whole thing to pull it back out later. But that's kind of an interesting academic sidebar. This is just like people are using space to generate blocks, but the blocks are small and quickly verifiable, and there's no useful storage going on here. You heard my opinion about useful storage for making blocks previously.
Hi. So engineers are notorious for over-engineering stuff. I'm hearing proof of time and alternating with proof of space. Can you briefly explain why the design is that way? Where
yes, it's because you need to stop grinding attacks and history rewriting attacks, and that's the only way to do it.
So for proof of work, you're using a lot of processing power to solve these puzzles, but for proof of space, you're pre-committing this space from the nodes that are currently in the network.
Well, you're not pre-committing it. You don't have to pre-announce what it is that you're going to be using later. Is an important one of the properties of the proofs of space. But you are doing work up front that you only have to do once, such that later on you can very rapidly, in response to any challenge, generate a proof of space for that challenge, or a set of proofs of space for that challenge.
Up front?
It's like 2 passes over your hard drive, maybe 3 or 4 if you want to squeeze another like 5% out of it.
And you're saying that like you're going to use this space on the hard drive for the mining?
Yeah, this is exclusive to using it for useful storage while you're doing it. So
So you can't do anything with this space?
yeah, so probably if you're doing this on a real storage media, you have a couple of plots set up, and every time you start to run out of space, you delete one of your plots. And
Will your verifiable function
Yeah.
be bound to hardware like proof of elapsed time that was developed by Intel, or is
no. This is not using proof of Intel. This is
it will be like hardware agnostic and can run.
yeah. It is a mathematically defined thing that it takes these inputs and has this output, and it does not require trusted hardware in any way, shape, or form. It does make assumptions that the fastest one of these things out there is reasonably commodity. And it definitely will be hardware acceleratable. But one of the design criteria for the VDF we're going to be using is to try to make it cost as little as possible to make VDF hardware acceleration that runs as quickly as it possibly can.
Given the number of Magic Bean projects that are out there with proofs of everything, what is kind of like your one-liner to go to for why we need to waste this a resource to secure a public blockchain?
So at a very high level, so the Wikipedia page on blockchains actually has a paragraph that actually explains what blockchains are, because I wrote it. Fundamentally, Bitcoin is a secure distributed database. It's very, very hard to make a secure distributed database because you have this fundamental problem that you and I might disagree about what the current state of the database is, and we have no way of resolving this conflict whatsoever. And a very large fraction of all these, I have this brilliant new proof of whatever thing, is actually going backwards. It's creating this problem again, that there's no way to resolve these disagreements. So the new innovation is the blockchain. Now, the blockchain is a very overused word at this point. It's being used to essentially refer to anything that has secure hashes in it. So, like, general rule of thumb, if your definition of blockchain makes Git histories be blockchains, there's something wrong with your definition of blockchain. To really be a blockchain, there must be some kind of proof of work in it. It must have some kind of a weight. And you and I, if we have a disagreement about what the current state of the system is, we compare the blockchains that we have, and the one that has greater weight wins, so the network as a whole can quickly come to consensus on what the current state of the database is. And that's the fundamental property that you need in order for a secure distributed database to work. And proofs of space and time does that almost as a swap and replacement for the proof of work. And basically all these other things are breaking fundamental assumptions that are going on there, including proof of stake. It does not have that property.
I'm not sure how to phrase the question exactly, but it's something like, or what property of proofs of space and proofs of time, or maybe property of current hard drives that we have, prevents another hardware arms race, kind of, that we had in Bitcoin?
Yeah, the idea is, so there's two different things here. There's the proofs of space and proofs of time. For the proofs of time, there's actually no overt reward for doing proofs of time. So there isn't much benefit to doing them. You can squeeze more utility out of your space, but someone, just to be a jerk to everyone else, can run a proof of time server just as a public service. And if theirs is the same speed as other people can't squeeze anything useful out of it. We are, as I just said, working on making it so that the actual R&D cost of making a good proof of time chip is going to be reasonable. And physics is kind of on your side here, that clock speeds, max out at like 5 or 6 gigahertz or something and are totally impossible to get faster than that because physics. Maybe someone can go faster using a gallium arsenide chip, which would actually be awesome. and I'm going to try, we're going to have competitions that we're going to sponsor for the best implementations of proofs of time, both in better software things and in terms of hardware acceleration. And the one we're going to be going with can be implemented well with GPUs. Not as fast as you can do it in hardware, but it's going to be pretty expensive to beat your GPUs. So we're going to make sure they're good implementations for the proofs of time with that. For the proofs of space, nice thing about storage is bits are bits. It all looks exactly the same. There's no difference. Like the only thing you're optimizing for is the number of them. And the only parameter about how these things can behave a bit differently has to do with like latency of lookups, right? For CPU operations like multiplications and SHA-256 hashes and things like that, there's no, those are all completely hardware acceleratable. Like you can always come up with some hardware that will do it faster than other things. For storage, all the storage needs to do is store data and be able to retrieve it again later. There's no special magic thing to be done.
But with the latency of lookups, is there a significant difference between an SSD and a normal hard drive?
No. The difference between an SSD and a hard drive is pretty much immaterial here. It's probably going to be like a second of difference, and that's at the margins. You would prefer to not have to use that second, but it's not going to make the difference in it. You can just as well farm with either of those. And as far as the system is concerned, they're pretty much the same thing. The only things that come in are like tapes, and tapes just get mauled because of their lookup times. Their lookup times are way too big. But if your lookup times are like on the order of 10 milliseconds, even if they were like 50 milliseconds, that would probably be fine.
Thanks.
So this work of proof of time and space, do you see it as something that is going to be unique to Chia, or do you see it as something that like, oh, we've built this and now others maybe adopted this, like let's say Ethereum deciding that they saw the light and they want to adopt it as well?
Yeah, there's nothing particularly stopping other people from adopting the exact same proof of space algorithm as we're using, and then people would be able to use those things using the same proofs of space allocations that they have on their hard drives already, as this kind of implicit merge mining, where the two things merge mining don't even have to know about each other. They have no coordination necessary whatsoever. Might be a good idea for other people to do that.
And another question, scalability-wise, Chia is going to be like a peer-to-peer like digital cash system. Like, what's your defined mission for it?
Scalability-wise, the plan is basically Bitcoin's plan. You go to
Lightning?
Yeah, you go to net settlement with Lightning. You do some new tech for net settlement that we haven't completely worked out yet. That's being worked on. Do a bunch of smart transaction stuff for better custody arrangements, which people haven't worked out yet. We're making Chia be a better platform for smart transactions, so that'll be easier to do in Chia. That's basically the plan. Its nominal throughput is going to be pretty similar to Bitcoin's, just because you want the cost of running to a full node to be under control.
Anyone else?
Which programming language are you going for your initial implementation?
So the initial implementation is probably going to be mostly in Python, with the parts that really need to be performant written in C, and available libraries written in C to speak like the SPV equivalent protocol, so that we can integrate with wallets, so existing wallets can easily integrate with us, and things like that.
Do you see a competing implementation in competing languages live on the?
Yeah, we would really like to be in, all the major languages. It's just from a practical engineering, getting stuff out the door point of view, our minimum viable product probably involves most of the code base only being supported in Python on initial launch.
Are you worried about consensus bugs arising from various implementations?
So, every time I start digging into the details of Bitcoin protocol, I come to the conclusion that if I'm worried about consensus, it's much, much better for me to write something new from scratch than to start with the code base that Bitcoin has. That's a really, really bad code base in horrible formats.
I'm saying he's not Satoshi.
I have a lot of experience making protocols that interoperate reliably among multiple implementations, and that's really about having a very nailed down, well-defined, simple protocol. And that can totally be done, and writing it in Python is about as good a language as any other for having a simple, well-defined set of data formats and behaviors.
Just a point on that, if any of you write in Python and C and are interested in working on proofs of space in proof of time, we are hiring engineers. We've hired 4 this month, and we'll be hiring more this year.
So you mentioned that people are not going to be using this for storage, so what are people going to be using Chia for?
So the Chia proof of work block creation thing is just going to be its own animal, its own thing utilizing people's excess stuff for. As far as using Chia, the idea is to be a better Bitcoin. We're really going after like banking as a use case just in general, because that's the obvious thing to do, and in order to support that you need to have better support for transfers and custody arrangements and those kinds of things. So that's going to be the emphasis of development moving forwards.
And sorry, just a follow-up question on that. So do you have a roadmap or a plan for how to get adoption and sort of replace Bitcoin or any other medium?
Well, the first thing to do is launch a product with the basic feature list. And that's what all the emphasis is on right now.
Thank you.
Well, other questions?
I can just yell out. You were talking about the signatures and using Z-SARCs for full proofs. Is that with regards to proving identity?
Oh, the zero knowledge signature goofiness that I was talking about, that is just for block creation. That's the only place we're going to be using that, because there you want non-outsourceability, and that's an important feature. We're not really going to be doing any like Zcash or Monero type features out of the gate. No, we might add confidential transactions in the future. Probably we'll get them at about the same time as Bitcoin gets them, using about the same techniques of like having an extension block.
Because of the cost of implementing it?
Yes, basically it can be done later, and the technology for doing that is a moving target that's been improving, and is a lot of engineering headaches, and is not crucial that we get it done day one. So we're not doing that right off the bat, and possibly not for quite a long while. Our basic signatures are going to be BLS signatures, which are a little bit bigger at reasonable security levels and a little bit slower in some ways, but have a lot of nice properties. In particular, they're non-interactively aggregatable. So you can require that they be aggregated. So like Schnorr supports aggregated signatures, but for Schnorr, people have to do something in advance to make aggregated signatures. And if you're trying to save space by using Schnorr signatures in a block, now you have this whole other set of headaches of having to specify how the signatures are aggregated together in your metadata and verifying all that. Where with BLS signatures for a single block, you can just have literally a single aggregated signature for every single transaction in the entire block, and it just works. Which is a very nice property to have, and a lot of other smart transaction stuff winds up just being a lot easier because of its extra mathematical properties. So we're going with that.
So, what's the next question?
I'm just curious, like, in the future, will it be harder to mine a block?
Can you speak up just so the mic?
Yeah.
It'll be harder to mine a block with proof of space and proof of time as the network grows, like sort of like Bitcoin's getting harder and harder to mine coins.
Yeah, there's work difficulty resets, but operate the same way. So the aggregate rewards that are handed out by the network are fixed based on the amount of time that's passed and the transaction fees that are being made available. And so if you're sitting there farming and then 10 times as much capacity comes online, you'll be getting 1/10 the rewards you were before. That's just the way the system works.
If the farmers are obfuscated by zero knowledge signatures, where do bots, I guess, if you have access to people's storage, how do you stop those people from using that free storage for money?
Botnets are bad.
Yeah.
When you're doing proofs of anything, you basically have two options. You either favor botnets or you favor ASIC miners. Like, it's sort of like, which of these two groups do you think is more evil? Seems to be kind of a toss-up. There's pretty strong competition in this game. It would be, if a miner is willing to start deleting a user's files in order to farm better, anyone who's willing to do that is better off trying to make money running ransomware than trying to farm off of it. And if they don't want to do that and they just want to go, okay, I'm just going to surreptitiously make some extra files that aren't visible to the user and farm off of that, it's not actually going to be hurting the end user all that much. So, not the end of the world, but mostly people need to secure their stuff so it doesn't get taken over by botnets.
Cool. Question? I had one. Anyone else? Yeah, can you share a little bit more about your timeline? So you mentioned some pretty exciting things like competitions, but when will that happen?
Yeah, we're hoping to actually launch the network in like a year, but we'll see how it goes. You know, it's software. Scheduling is hard. We'll have competitions probably long before that, but right now we're in the early stages of de-risking everything, and we have like fewer programmers than like gigantic projects right now. So we're doing more hiring and getting underway and doing a lot of fundamental work on what are the algorithms that we're doing and stuff. But in the coming months, much more tangible things will be coming out.
So you guys stay tuned because we will be sharing all the jobs and opportunities too. Other questions?
Great talk.
Wait, Rob? Oh. Okay, cool. So yeah, this is super early days, so really exciting. Any other comments from your team? Okay, we are going to be south side around the corner, just on the other side of Tehama at Howard. Come by, and we'll be chatting some more about this. And then, yeah, join us on Telegram, and we'll talk to you guys on that channel, and then in 2 weeks at our next talk.
Oh, also, Keybase has Chia has a Keybase channel.
Yeah, we have a Keybase channel that you can come on and ask questions there, and also there's lots more information on chia.net about our technical stuff.